record. So welcome on in, and happy Thursday. So for those of you that made it this far, I'm pleased to announce that you are finished with halfway through your course. So, yay. Okay. Just a reminder that the test will be next Friday. So not tomorrow, but the one after that. We got a lot of stuff to do today. First off, we're gonna go ahead and cover everything you need to know about floats and how to interact with them in x86. So we'll cover all the basic operations that we've been doing with the normal integer registers. Briefly talk about quiz 4, which I posted up not too long ago. I think that's correct, right? 1, 2, 3, 4. Yeah, so 4. Quiz 4. It's relatively simple. Cover everything that we've gone over this week, up until floats. So you might have, I think, some questions on floats. Nope, just one question on floats. This one is worth 20 points. So usually I want to give out 2 quizzes a week, but since it's already the end of the week, I decided to just put some extra points in here. So it is a 20-point quiz covering everything that we've gone over. Give you a lot more written response to help you get prepared for your test. So these are kind of what we might be looking for on a test, and we'll go over that maybe a little bit later after we cover the lecture topic. Next exam is Friday. Yes, so if we pull up our calendar, it should be on the 2nd, right? It's Friday the 2nd. And then your final exam is going to be on the 9th. So we don't have a lot of time left in the class, but thankfully we've already covered most of the material that is on our syllabus. So if we pull a syllabus over here, we've already done most of these. So command line was yesterday, floating point today. I might go back and revisit toolchains a little bit more, but this isn't like a full day lecture. So on Friday we'll more or less have a little bit more review, or maybe I'll start on the system services, and that way we will be able to finish the lecture topics all the way until threading and race conditions. That way you'll be prepared for your test, and we'll have an extra day, say maybe Thursday, to review for it. So we'll see how the pace of the class goes, how many questions you guys have, and how well you're doing on the quizzes and the homework. So we'll see how it goes. But for today, let's go ahead and wrap up by finishing floating point values. Okay. So the test is going to be similar structure. We're going to be worth 150 points, but it will cover everything from functions all the way to threading. So everything this week and next week will be on the test. Of course, there might be some cumulative concepts, like you might need to know how to move and add things in order to do some of the test questions. But not specific. We won't specifically be asking questions on the first exam. Okay, so let's go ahead and talk about floating points, floats, floating points. Okay, so far, if you remember, like all the registers that we've been covering, right? RBX, the R8s through R15s, all of those, these are int-based registers. So you never really see decimals or floating point values being used. Okay, and previously we've also covered IEEE bit floating point precision, so you should more or less know how the machine interprets floating points. Okay, so these are your integer-based registers. When we deal with floats, we have to have specific registers designated for them. So what we have instead are these float registers. Okay. And they're quite simple. You get 16 of them, and they all start with XMM and then some number between 0 to 15, making a total of 16 registers. So I have XMM1, XMM2, and then all the way down to the 15th. Okay, so you have a total of 16 of these registers. Okay. And each one of these registers, so if you look at an arbitrary one, so like XMM0, for instance, just like the normal registers, but these are all 512 bits. But in our class, we'll primarily be only using the later 32 bits, maybe 64, but for most general cases, we'll only be using 32 bits, which encompasses a large amount of data values that we can achieve. But if you're interested, sometime in the future, maybe if you are working in assembly, these registers are capable of storing up to 8 floating point values. So we can subdivide these into 8 blocks to store 8 floats. But we will not be using this kind of architecture in our class. So instead, we'll be only using the last 32 bits, and I guess pretty much the rest of these are all what we call wasted because we won't be using it, but that's all right. So for example, maybe, is that capital XMM or no capital, or lowercase, just like your registers. So some practical applications of using these floating point registers that utilize all 512 bits might be some high-end graphics, maybe that uses a lot of calculations. They might choose to store multiple floats in here at a time, or use the entire 512 bits. But we won't really get into that, but we will be using it for some basic operations. Okay, so that is generally the structure of the register. Okay, so remember, so I guess this is a quick recall. We have the move, destination, and the source, right, for our integer-based registers. But, I guess we'll use I for the integer base and float for the floating point registers. So in this case, we have move S or P, S or D. Then we have the actual destination and the source. So this might look very complicated. Essentially, you're just picking either S or P here, or S or D here. So the first S, we'll call this maybe S1, 2, right? So the first S represents single. That means you are using a single part of the register, and the P stands for packed. So if you want to use the full 52 bits, you would use the P. Okay. We will probably never touch the packed version of the register, so in most cases we'll be using S. Okay. The second one, so if we have S2, the second S stands for single, which means that you want to allocate for a float, which is 32 bits, or D for double, which is 64 bits. Okay. So some things that we might want to keep in mind is that some general rules still apply. So destination and source cannot not both be memory. Okay. So same rules apply. Only either can be memory, but not both. Again, the destination cannot be an immediate. Okay, so no values. But then a third one, this is kind of like the new one. That is, you'll see this reoccur a lot when we deal with the floating point registers, is that the source cannot be an immediate as well. So neither can be immediate, which is different from our traditional integer-based register movement. So, but other than that, the same rules apply. So the source gets copied into the destination, right? The source does not get changed, but the destination does. So, okay. So maybe for example, let's say I defined something like f0 in my dot data. We gave it 32 bits, hence the declare double. And then let's say we just assign the value of it 0. So if I wanted to move this value in, I could maybe do something like move. So S for single, right? So single means I'm only using the last part of the register. And then S again for if I want to have a single float. So move SS X M M O or 0 D word because it is size 32 and then the variable name. So it shouldn't look too different from what we're used to seeing, except now we have this extra bit for our floating points. Let's go, for example, maybe we have F10, and then let's use a quad this time. So we're allocating 64 bits. So this is maybe sometime when you would use the SD for single register and double for the amount of bits to allocate. And then maybe one. Oh, not D word. This time it's Q word because it is 64 bits. So Q word F10. Okay. And then same rules apply. You want them to be the same size with the destination and the source. Okay. So should all be quite familiar, just minor differences. Are there any questions before I move on? Because generally this is the structure that we'll be following for the rest of the instructions. So since you guys are fine, we can maybe move on to the arithmetic instructions. So it will always be move S, and we change the last letter. In this class, because we are not going to be using the full 512 bits, yes, that'll be perfectly, that's a perfectly valid thing to assume. So it'd be move S, and then you would replace the last letter, either S or D, depending on the size of the variable you want to, or size of the register you want to be using, either 32 bits, which is single, or 64 bits for a double. So for this class, this will always be S. We'll probably never use P, but it's good to know that you can also set it to a packed register. If move P, do you still need to choose SD? Yes. You still do, because it will you will basically tell it whether or not you want to use this much data or like this much data out of it. Actually, yeah, yeah, I think still do. You want to be able to know how much data you want to store in. Okay, so moving on to arithmetic, so floating points. So remember, for our standard arithmetic, we have add destination source, right? And then for floating points, very similar to the move instruction, we have add SP or S or P or S or D. Then we have our destination, and then we have our source. So very similar. So for example, you might see something like add SS, right? Or SD. Now it's confused. Okay. So same and similar rules apply, right? So we can't, both cannot be memory. So essentially, I will be able to copy paste this and maybe call this the golden rule, right? So now same things apply here. Right, destination source cannot both be memory. Destination cannot be an immediate, and the source cannot be immediate. So these two should carry over from our previous instructions, and the last one is just we cannot define our own values for our source. So it has to be placed into a register in order for it to work. That's just how the architecture works. So we just have to follow that. Okay, so for example, maybe we have in memory or in data f0. Maybe we have maybe let's not use 0. Let's add by something. So maybe f1. Let's use d words. So 1.0. So if you wanted to store floats, obviously you would need the decimal. So f2. Maybe we have 2.0 this time. Okay. So maybe we can move SS. And let's go ahead and use a different register. So maybe XMM2. And we'll pass it or have it copy the value. Of course, I have to dereference. So make sure you dereference your variables if you want to access the value of your variable. And then we can call a simple add SS. And then maybe I want to add it and store it into my my second register. So, and then maybe I want to add F1 to it. So in this case, the result is that XMM2 will be storing the value 3.0 inside of it. Okay. So it shouldn't be too difficult. Let's go ahead and finish off the rest of the operations. And I'll preface this and say that you'll like multiplication and division a lot more using floats. Okay, for subtraction, so I'll just write the integer one first. So just to refresh your memory, remember that adding and subtracting are essentially the same. And in integer adding and subtracting, we don't care whether it's signed or not signed. In general, for floating points, they don't care at all whether it's signed or unsigned. The instructions don't change. So let's go ahead and say sub SS, or it's the same syntactic. syntactic SRSS, SP, SD. Okay, then we have our destination source, same thing. Okay, same golden rule applies. And then we say sub. Let's just say our XMM2 was still the values of 3.0, just to continue our register use. So XMM2, and then maybe we say dword. We defined F0 earlier, which is just 0, so subtracting 0 doesn't really do anything. Subtract, aha, sub SS 2. Actually, let's store it into a register. While inefficient, at least we'll show the use of the register a bit more, or the move instruction a bit more. Let's move in F1, and then we can call sub SS XM 2 3. That right? So here XMM 2 is 3.0 minus 0, which is 3.0 still. XMM3 gets the value of 1.0. And then here, XMM2 gets the value of 3 minus 1, which is 2.0. And then XMM3, because it's the source, does not change, so it remains 1.0. Your head hurts. Well, I'm sorry to hear that. Hopefully, these instructions aren't too painful since they're very reminiscent of their integer counterparts. Okay, so remember in the mul instruction, we have imul and mul depending whether or not the operands were signed or unsigned. Here, we don't care. So for multiplication is rather simple. So SS or SD. That. And you don't care whether it's signed or unsigned. And what's great is the remainder is not stored in a different register. Yes, I can scroll up. The remainder isn't stored in a register. So remember, in I guess you wouldn't have a remainder in multiplication, but in this case, the solution would be stored into 2 registers, right? So usually a D and an A register, or if you're in the bytes, it'd be AH and AL. Here, there's none of that. It will all be stored into 1 register. So it's nice. So let's say maybe mul SS XMM2. Right. And the one caveat to this one is it's still a destination source. So very similar to adding and subtracting. Here in the integer version, remember, it will always be multiplying by the A register, which is a little bit inconvenient sometimes, but it is how that is. But here you can actually follow the same structure where you define a destination and a source to multiply by. And then same thing, the golden rules apply here. So what's good is there's no register restrictions, and there's no type changing from signed and unsigned. So all you have to do is just say maybe dword. Let's go with F2. Okay, so this is 2 times 2, so XMMO is equal to 2.0 times O, which is 4.0. Okay, and then I'm going to do a sub instruction so I can set up my division and show you what dividing something like 3 by 2 might look like. So sub XMM2 word F1. Is equal to 4.0 minus 1.0. we know it's 3.0. Okay, so very nice. There is no restriction on register. So in this case, we do not need to use a designated A register to multiply. We can assign any register as a destination. And there's no type changing between signed and unsigned values. So no need for the imul, no need for imul ss, just simply mul ss. Okay. Same thing for division. So remember division, we took 2 registers and then we had to divide it by some operand, right? This is div and idiv. Right? Okay. And then the remainder is stored into RDX, right? So remainder is in the D register, and then the quotient is in the A register when we finish. But in division for floats, it's a lot nicer. Right? So similar thing. We have div s p s d, and then tactically the same, so a source and a destination. And then let's say, for instance, I want to divide x, divide single xmm2 by 2. So our current xmm is 3. So f2, what's nice is u equal to 3.0 divided by 2.0, and it is what we expect it to be, 1.5. So no need for another register to store the remainder, because now we're working with decimals, and that's what we would get. So if we were doing it in this version, we would get 1 remainder 1. And the 1 here will be stored in D, the 1 here will be stored in A. But here we will have a nice decimal. And of course, the golden rule applies. Destination and source can't both be memory, and neither can be an immediate value. Okay, so is there any questions about, so someone says, how does it know whether or not you're using a positive number or a 2's complement of a number? Remember, when we go back to IEEE 32-bit floating point precision, you learned exactly that the first bit, okay, remember, recall IEEE, not 23-bit, 32-bit floating points. We represent floats as such, right? Remember, the first bit is for your positive or negative, right? So when it reads, and then we have the biased exponent and then your fraction, right? So when it reads this, right, it knows that the first bit is for the sign value, so it knows exactly what to do. Okay, yeah. So that's why we had to learn this in the beginning. It was just part of our data representation, but of course we didn't deal with any floating point values until now. So, but don't forget that the machine utilizes this notation, this architecture, to read in floating points. So maybe I'll put in another IEEE question on the test, since that might be good to remember. But we'll see. I'll try not to put in. I'll try not to make it a cumulative test, but some concepts might tie into each other. Okay, so are there any questions about the arithmetic operations about or on floating points? So hopefully they all look very simple to do. You're just basically appending this S or SD in our class. Maybe in the future, if you do use assembly or you have to convert something to assembly, you might see the packed version of the register being used. But hopefully not too bad because you don't have to deal with this annoying two register saving the remainder, all that stuff. The final exam is cumulative. I don't want to make the final exam cumulative because there's a lot of content to pack in to a very small amount of points. If I do end up making it cumulative, I might just include. Actually, yeah, maybe I'll make it cumulative just because the MIPS part of the course I don't think will amount to a whole test by itself. So maybe I will make it cumulative actually. Um, is MA going to be on the exam? I don't know what that is. Um, but just expect the stuff that I emphasize in class and the stuff that are in your quizzes to be related to your exam in some degree. When we get a MIPS assignment, I plan to give you a MIPS assignment, but it's very difficult because MIPS is on the last week, which means I will need to sign the assignment before you even learn about MIPS, and then as you're learning about MIPS, you can complete your assignment. And then, of course, you probably need to finish it before the final exam starts on that Friday because grades are basically due the day or the day after. So it's very rough on time, but I want to give you a MIPS assignment. So we'll have to see. For now, just pencil in you will have a MIPS assignment. Will we get a lecture in time travel? Maybe. If we have time, I'll teach you about time travel. So now that we know about floating points, do we need to use the int registers ever again? Yes, you still need to use the int registers. Remember, addresses are defined in terms of your int registers, right? Can't really use floating points for those. The way your architecture works, right? Your RSP pointers, your RBPs, your RIPs, and stuff like that, they're all int-based registers. If you want to do modulus, right, you can't really do that. I guess you kind of can, but you might get in. Your results may vary depending on how precise the numbers end up being. But remember that floating points lose precision over time. For mul div add sub, we can just use floating points. That's not necessarily always true, right? Because if you wanted to do modulus, it's a lot easier to just bring out the remainder from the integer division. If you don't need any decimals or precisions, it's usually not necessary to do that. But we still have a lot of stuff left to cover over for floating point register use. So we will you'll see, and then I've devised a small code to kind of show you how you can use both of them in the same program. But let's just finish off all the stuff we need for floating points, and then maybe we can discuss the viability of just using floating points. Okay, so one thing that's important, and this pertains to the architecture. Hopefully the stream did not freeze. Okay, yep. Okay, so one thing that's important, so maybe this could be a test question, who knows? You cannot operate on mixed data types. So, i.e., int cannot operate with floats, and floats cannot operate onto ints, right? So you wouldn't be able to do something like add a register. Let's use 32-bit. So EAX and say XMM0. You wouldn't be able to do this. This is not legal, right? So any operation regarding a int-based register and a float-based register or data type, because this could be memory, this could be whatever, is not allowed. So what needs to happen is we need to convert. So maybe in C++, what you do is you would multiply the integer by 1.0, for instance, right? And then if you wanted to convert a float to a double or to an integer, you usually would truncate and lose your precision. But if you really wanted to use an integer there, you could. So what happens in C++ is you might think that C++ is trolling you when it says you have to or that you can't do these mixed operations on different data types. But it's actually because the architecture just doesn't support those types of operations. And you'll see that so C++ is not trolling, right? And that's simply because the architecture does not allow, right? So you wouldn't be able to do like int x equals 2 float y equals 1.0 and do something like z equals x plus y, right? You'd have to cast this into either or and then get the result as that. But we do have some things that will aid you if you do end up needing to do operations between an integer and a float. So these are your your conversion operations. So conversion instructions. So okay, and there's 4 of them. So the first one we'll talk about is CVT SS2. Yes, there's a 2 in there. SI. And then you will give it a register and you'll give it a source. The thunder here is so bad, my internet might go down. I'm sorry to hear that, but remember, the lectures will be reposted on YouTube after the second class. Yeah, and you can always feel free to join the second class. If you do get thunder or your internet goes down during a test, make sure you contact someone immediately if possible, so we can help arrange for something if needed. Okay, so conversions. So convert. So CVT SS to SI. So very similar syntax, right? To our move commands. So let's kind of break down what this is saying. Essentially, you want to convert a 32-bit floating source, and it's a floating point source, to a 32-bit int destination, right? Okay, so the destination must be a register. and that's why we use reg instead, but this is technically your destination. Be a register. Okay. And then the source, again, cannot be an immediate. So no values allowed. Okay. And we will also call this our golden rule, right? So for any of the conversions, this rule is still going to apply for them. So let's see, we have, so this is if we have a 32-bit floating point that we want to convert into an integer. So here's an example. I'll do 3 legal ones. So XMM, oh, I forgot my convert. So convert EAX XMMO. So very valid, right? So register destination, a floating point source into a integer. Okay. Same. Oh, I didn't do the last part of that. So CVTSS2SI, like that. We can do CVTSS2SI, say EAX with a memory. So let's say maybe we defined our float 0 from earlier, right? We can pass that floating point and make it into an integer. So those are some examples of what you can do. Let's go ahead and do the next one. So CVT, this time is SD to SI. Then this one takes a similar syntax, so a register here and a source here. And this one will convert a 62-bit floating point source to a 32-bit integer. And usually we aren't able to do something like this because we're storing more information into a smaller register size. But in this case, it'll just truncate. So same thing goes. We will have the golden rule apply. So destination cannot be a register, source cannot be an immediate. And this one will probably be rarely used. Usually you'd never go. So we have CVT SD to SI. Maybe we can. Excuse me. So maybe we want to convert, say, same thing, right? But instead of using the 32 bits of XMMO, we're going to be using 64 bits instead. So you can also maybe even do something like CVTSD to SI, XMMO, XMM1, like that. So basically, we take the floating point, the 64-bit floating point source, and then we store it as an integer inside the floating point register. Okay. Also rarely used, but might be useful sometimes depending on the circumstance. We also have the SIs to SS. So this is the opposite. This one will take a 32 bit int source, integer source to a 32-bit floating point destination. Okay, golden rule applies as well. And then I'll also just squeeze in the last one here, si to sd. And instead of this being the 32-bit destination, it'll be a 64-bit destination. So get register source, register source. So we'll be using 64-bit as our destination sort for that. And these must be your. I guess we can write it like this. So we call it RX DST. So these are the registers exclusively for the floating point registers. So here, in addition that it must be registered, it is RX DST is the floating point register. Okay. So examples might be convert SI to SD X. Oh, don't need the XMMO, and let's say EAX, or convert SI to SD RA. No. Something like that. So these would all fine. Make sure that these are 32-bit. And that is more or less how to convert. Are there any questions on the conversion commands? Maybe I'll zoom out a little bit. So let's see all it's here. So it shouldn't be too bad. These are just useful if you want to do operations between integers and floats. You'll need to do a conversion before you do that. Okay. So, there is one nifty little thing we can also do. I think this is also built into the register. So either SS or square root SD. Zoom in a little bit. So this one will take in a register, so RX dest, and a source. So here, the source must be a floating point. So, and of course, RX DST has to be a register, a floating point register used as a destination. And this operation essentially takes the square root as a square root function. So that's a little bit nifty. If you want to see a little bit more documentation on it, you can feel free to look that up. What's RX DST and RX cast? I don't think I use RX cast, so maybe did I misspell something? RX DST is basically let me just write it on the other notes right here. So colon. So here RX DST is equal to a floating point register. So any of your XMM registers. I don't think I used the word cast, so maybe okay. You misread it. Okay, so it's okay if I misspelled something or used a wrong operation. Feel free to catch it and let me know. Okay. So yeah, there's more documentation on this somewhere in your textbook, or you can look for it online. But that's just a cool thing that's also, I think, built um, into your architecture. So this is just the square root function. Okay. And otherwise, you would have to use a very arduous function call for it, which it's just not pleasant to implement. Oh, it's not too bad, but it's still like more work than calling a one-line instruction. Okay. So now let's talk about your comparisons. Okay. So comparison. Remember, we had CMP, op1, and op2 before, right? So remember that the operands must be the same size. But in this case, the CMP function, or the CMP instruction, excuse me, does not work for floats or for floating point registers. So instead of using the CMP, we have to use something like U compare SS or U D. Okay, and they both will take a Rx source. So we call them sources because the values of these operand, or well, this register will not change. Okay, and some kind of source value as well. So some things to know about this specific instruction. So here's the integer version, and here's the floating point version. Some things to know is that they have to be the same size. So no change between the comparison function and the U comparison function. They both have to be the same size. Both will set R flags. So R flags is still being used here for comparison. Neither is changed. And this is true for both comparisons. Here, Rx source is the register. So the XMM registers, call them. Okay, and then the one thing that's new, right, is the source cannot be immediate. So here, the CMP, we can do something like compare RCX to 0, right? So here we can use immediates as one of our comparison values, but when it comes to the comparison for say XMMO, this is not legal when using floats. So no immediates. In general, you cannot use immediates other than moving them into a register. So no using immediates in most instructions. That's generally the rule. Okay, and so with floating points, they're all signed values, right? Because remember, our AAA format, we save the first bit for the signed value. So we have to use the signed jump instructions. Okay. So remember that J, E, and J not E, or jump equal, jump not equal, don't care whether it's signed or unsigned, so that's fine to use. But we'll need to use JB, JBE for jump below and jump below equal. Of course, we have to jump to our label. So, okay, so this one works for both signed and unsigned. This one is the signed version. And then same thing, JA and JAE to a label is for signed as well. So just remember that when we're using floats, because of the IEEE, the first bit is signed, so it tells you whether it's positive or negative, and then you get all that stuff, and that's why we need to use the signed representation for our jumps. Okay, that way our flags will be able, well, that way we'll be able to tell what our flags is outputting. Okay. Okay, so we covered conversions and comparisons. Is there any questions so far before we top it off and talk about how we can pass them as arguments in the standard calling convention for functions? So hopefully that's okay. Let's go ahead and talk about some function passes. So maybe before that, we can do a little bit of review on the standard calling convention. Unsigned the same? No, floating points are always signed. Floating points are never unsigned because the IEEE convention says that the first bit is to tell what sign it is, whether it's positive or negative. So always signed. Okay, so the standard calling convention, remember we have preserved registers, right? So we have RBX and then some other ones like I think R12, R13, so on and so forth. We have our arguments that are pushed on the stack. So remember our arguments, the first 6 go into RDX. Sorry, not RDX. Ooh. RDI, RSI, RDX, RCX, R8, and R9. Okay. And then the stack afterwards, right? In reversed order. Okay. So if we look at the standard calling convention when we're dealing with floats, so floats, right? You'll notice that there are no preserved registers. Oh, and then return value is REX. So when we're dealing with floats, there are no preserved registers. The arguments that are being passed are going to be XMM0 all the way to XMM7. So you'll basically be able to pass a total of 8 arguments before needing to use the stack. And then the return value is going to be stored in XMM0. Okay. And if we were to have a function that passes both an int and a float, so maybe something like, and we want to return a float, so maybe we have a float, our function is maybe f1, and it takes in an int x and a float y and something, and then maybe it returns return y or something like that. some code. Standard calling convention will tell you to move the value of x into RDI. So move RDI. Let's assume that x was a C++ int, so we'll use EDI for 32 bits. Keyword x, since I couldn't come up with a better variable name. And then we would have to move xmmo. Let's also assume this is 32 bits. Then use y here, right? So notice that my first argument is here. My second, this is second argument, so I should be using xmm1. So my second argument ends up being passed as such. And of course, if I have more arguments, I will follow whichever. So this would be first, second, third, and this would be same thing, first, second, third, all the way to the eighth. So depending on the order of my arguments, I will have to use the correct register to represent the place of the move SS, correct? Yes, move. Thank you for catching that. Move SS. So yeah, depending on the location of where my argument is, I will need to use the correct register for that. Okay. And then, of course, if I wanted to store the value of that, right? So maybe move SS keyword and x and o. So maybe here was the call to f1. And then once it returns, maybe you want to store the value back into a variable. Okay. So hopefully that is the standard calling convention. So nothing really changes, except we now just have more information about what registers to use, how the arguments are passed, and what holds our return value if we're returning a float. Okay, so hopefully that's nothing new about the standard calling convention in terms of what we do in terms of argument transmission. But now we just append the rules on top of using floats now. Okay, so maybe let's do a quick example of some code. So maybe in .data, I have some list. Let's make them D words, so double words, and then there's some numbers in the list, right? It doesn't matter what those numbers are. We're not particularly interested in that. Maybe we have a variable called sum. Let's just initialize that as maybe we want it as a float, or maybe we want it as an integer. Let's do that. Use it as an integer first, and then we have an average variable, and then this one will have as a float. And then maybe the length is an integer because so this is the length of the array, and it is some value, right? Maybe it's 4. Okay, so maybe what I want to do is to make a loop that goes through this array, totals up the sum, and then maybe I'll pass the sum into a function that will calculate the average for me. So, okay, so how do we do that? So maybe first things first, maybe we want to initialize our loop counter. So length we know is a D word, so we'll use 32 bits on our register. So EAX, D word, and then length. Okay. After that, maybe we use RBX to store the address of our list. Maybe just to, should we use floats here, or? Yeah, let's use floats here. So let's say f list and assume all these values are floats. So we'll say f list. Okay, so that is the address of my my list of floats. And all of these floats are 32-bit because we're in size DD. Okay. Now let's go ahead and maybe move RSI as 0. So maybe I'll use RXI as my index. Okay. And then we can do something like move SS. Well, actually, I can't do that because the sum is an integer. So what I can do is maybe move my sum into, say, this should be ECX, by the way, because we're using a loop. So ECX, and then maybe I'll use EAX this time to store the sum. And maybe I want the sum, because these are all floats, to be a floating point, so I can do a convert, right? So maybe I do CVT. So I want SI to SS because it's 32 bits. We'll convert, so our destination will be the XMM register, okay? And the EAX is what I want to convert. So here I'm basically saying E is equal to, say, EAX times 1.0, which will convert the number into a float. Well, it's the equivalent, and that doesn't necessarily do this operation, but that's the equivalent of what it might look like. So, and then let's go ahead and loop. So OP and these bots. So let's go ahead and create our loop. So maybe we do something like add S. We're using 32 bits, so SS. XMM. Let's make our destination a different register. Don't know why we do that, but just for practice, we can mess around with some stuff. Actually, one thing before we do that is I need to maybe up and store the value of the next item in the list. So maybe you do move SS. So maybe we let's put our sum in. Let's not use this one. Let's put this into the second register. So 2. Let's go ahead and say, so we want a D word from my address, which is in RBX. My current index is 0, so this should give me the first value on the first return. And then each one of these is size 4 bytes, so times 4. And then we will store the item in the list into XMM1, or I guess we can, no, that's fine. And then we just need to add, well, we can just add to the sum, the running sum. That might make more sense. So we'll add this to the running sum. So this will get float from address, and this will add value that we previously got into our sum. Okay, that looks good to me. And then maybe we increment RSI so that we'll get the next value in the list, and we will loop our loop. Okay, so RCX will be decremented, and then we'll run the loop the length of the list, which is 4. And then what we should do is store the value maybe. So maybe we want to store move SS eword sum, whatever it was in XMMO. So maybe something like that. It's kind of running out of space. Let's go ahead and grab. Let's go to move this over to a new layer. Yeah, so now I've stored the sum. Does the sum need to be dereferenced in line 4? Yes, the sum needs to be dereferenced in line 4. Because I want the value of the sum. Good catch. Yeah, so whenever you want the value, you want to dereference. Okay, so maybe somewhere down here I want to call a function for the average, right? So maybe I'll call a function, find the average of a float. So I should pass it some parameters, maybe. So what I can do, let's see. Well, XMMO is already my first parameter, and it still has the running sum, so that should be fine. So maybe I need to do is move my second parameter in. So maybe I want to move RSI, which I don't need anymore because I'm outside of my loop, the length, right? So the length would be dword lang, and I should use ESI, not RSI. If I want to be extra pedantic, I can set the entire register to 0, entire RSI register to 0 first, but I don't need to. And then if I call my function, it should be fine. I don't have any stack-based arguments that I want to put. All I have are just my 2 arguments, which is the XMMO and the ESI that's already there. So when I call this, it should give me the average back into XMMO, and then I can do move SS dword. Let's say we have, do we have an ANS? We have an average, so AVG XMMO, like that. And then should be fine. I don't need to do anything in my standard calling convention because I'm not utilizing the stack. There's no need to update my RSP. Everything should be done for us. Okay. And then maybe in my function, we call it what? F average? F, and then let's give it a label. And then, so I already have my 2 parameters passed in, so it expects the sum. So sum, and maybe you would do float sum, and int length, right? So just to be clear about documentation, we expect these to be our first and second arguments that are passed in. So maybe what I can do if I want to take the average, right? So the average is going to be sum divided by length. But I have a float and I have a integer, so I need to convert. So maybe what I'll do is I'll convert. So CVTSI to SS. I want it in a different register, so maybe XMM1. And then I want to throw it ESI. And then I can call my my div SS, right? XMMO, which is the destination, and XMM1, right? So I'm basically taking the sum divided by the length now, and they're both floats, so it's perfectly fine. The destination, which is my XMMO, is going to store the average. So good thing I saved the sum inside previously. So now I can return, and then return will pop RIP, and then I'll be executing this code next, which is to move the contents of XMMO back to the corresponding variable. So we can move XMMO values to memory even though it's initialized as an int. Which part of the code might you be pertaining to? Move XMMO values. I don't know where it's which part you're talking about that's initialized as an integer. Let's see. So, you're saying that maybe this should have been a float, but no. Okay. Yeah, you're right. This probably you would need to do one extra step and maybe convert do a CVT on you want S to SI, say EAX, that, and then store this as EAX. Yes, in my original example, my notes, I had declared this as a float, but I changed it for this lecture. But yes, you would need to store it. You cannot store an integer into a double or into a float, and a float can't be stored into an integer unless you convert it. Just be careful when doing that. But other than that, are there any questions about using functions while integrating floats? So hopefully this code kind of more or less covers everything we did today in terms of floats. So it went through. I guess we technically didn't go through variable declaration with floats, but it's kind of intuitive. You just write it as a floating point. We went through copying or moving our operands into registers and our registers into variables as well. We went through some arithmetic. So here we used add and divide. We didn't really use multiply or subtract, but they're more or less the same. We have, I didn't go through any jumps that utilize this. So maybe if I wanted to make the length a float, maybe I could write a loop that uses the comparison. But here I just used the integer version because it was easier. What else did we cover? We went through conversion. So I did a bunch of conversion in here. And then the standard calling convention for calling a function that utilizes floats. So hopefully all of that makes sense. Shouldn't be too different from what you've been already doing, but we just need a couple syntactical changes and one kind of conversion instruction in order to make sure that we're not operating on different data types. So yeah, the golden rule applies. You cannot do operations on mismatching data types like this right here. earlier was mismatching. It's a good catch. So, any questions on floating point values or floats in general in assembly? Get all of these, so maybe could talk about quiz for. Out of sheer curiosity, do you know the performance between floating and regular ints with simple operations? I'm pretty sure the integer operations over time will process a lot faster. It's just simply how the operations do or work, but it shouldn't be off by a terrible amount. So I'm sure it doesn't matter too much in the long scheme of things. But yeah, there's a slight performance benefit using floats. Using integers. Okay, so maybe we'll go ahead and take a look at quiz 4. Since we only have about 9 or so minutes left. There is roughly 11 questions, and this quiz is worth 2 quizzes worth of points usually. So it covers a lot of material. So question 1 says, what happens to the RP register when a function call occurs? So this should not be new. It's more a review question. So if you don't know this, you should maybe brush up on the standard calling convention. What happens to the RP register after a function call returns? So this is what happens after. This is what happens before. Question 3, pick the register that contains the third argument passed according to the standard calling convention. Okay, not too bad. Question 4. So according to the standard calling convention, what is the reason we push registers in the beginning of a function and pop them at the end? So this is primarily referring to something like this, or let's say in our function f1, right? F1, we have maybe we push RBP, and then maybe we move RBP, RSP, and then here, code, and then we do like push RBX, push R11, etc. So it's mainly asking why we're pushing these and why we pop them at the end. Your screen is still on notes. Oh, haha, very, very interesting. That was a trick to see if you were paying attention. So you passed. So hopefully the first 3 questions not too bad. Multiple choice. What happens when RP when function call occurs, and what happens to it after the function returns. Third one is the standard calling convention. What is the third argument passed? So you have to pick the register. Could have thrown in a floating point register, but that's not what really we're asking here. So for integers, what register we're using. Here is the, according to standard calling convention, why do we push registers in the beginning of a function and pop them at the end? So here's an arbitrary function that I just coded in the last 30 seconds. So it's mainly referring to why do we push these registers and why do we need to pop them at the end. So make sure you answer that. These are all written response. What is the purpose of the add RSP some immediate value after the call statement? So remember, we do our standard calling convention, right? It says to push or set arguments 1 through 6 in their registers. Then is to push 7 plus on the stack. And then after that, we call our function, so call f1, and then it's asking why do we say add RSP some value, some immediate here. This is what it's referring to. Question 6 asks, given the following code, write the code to output the message to the console. So I have or I guess I should have given you more because just assume that sys write and sys std out are defined for you. So maybe I'll edit this if you started the quiz already and it's not edited, then just assume that these variables are defined as well. So I left that out, but you should be able to just assume that they're written for you and use those. Or you can write the value of it. So if you want to look up the value of the operand, or the not the operand, but the system code for it, then you can do that as well. What is the stack buffer overflow problem, and what can we do to circumvent it? So this is a two-part question, so make sure you define what stack buffer overflow is, and then 2 is to provide a method. So remember when we talked about it yesterday and a little bit about the day before, what happens with user input. Make sure you define what the stack buffer overflow is. I can't count to 218. Oh well, that's not a coding problem. So unfortunately, I also cannot help you with that. Provide a method to prevent it. So it should be very simple. You don't have to go into coding necessarily. If you want to provide an example, feel free to do so, but I'm just looking for a simple solution. What software or entity is responsible for parsing command line arguments? We went over this, so hopefully you remember which one of these 4 is responsible for that. In question 9, so where is the argc value stored, or what register is it stored in assembly? So if you know your standard calling convention and you know what the arguments are inside of command line, then you should know which register it's stored in. And then the question 10 says, where is the address of the 3rd command line argument stored in assembly? Same thing. All you have to do is provide some sort of address. So maybe I don't know, RSI plus something might be useful. List the preserved floating point registers as defined in the standard calling convention. Basically looking for, let's say, like first argument stored in XMMO, and then so on and so forth. So quiz, it shouldn't be too bad. Most of these concepts aren't too in detail. I wish Windows was less grumpy and would let me use sockets. I hate having to write different code for different operating systems. Well, such is the struggle. You know what they say. It is what it is. Yeah, I wish I had a little bit more portability, but such is such, I guess. But hopefully your quiz isn't terrible. I think it's like half multiple choice, half written response. So should get you kind of more adjusted to doing more written response for the tests. Before I let you go, are there any questions about anything we've covered so far? Yeah, it do be like that. Yeah, that's true. It do certainly be like that. Don't have any questions about today's topics, that you're free to go. and I will stop the recording here.